Section 4.8 talks about row space, column space, and null space. Now, this is a crucial section. For a matrix m by n, the vectors r1 equal that vector. It's already darkened, so you know that's also a notation for r. r2 equal, r3 equal. These are called the row vectors. In Rn, formed from the rows of A are called the row vectors of A. And if you look at the columns, these are called the columns of A, and we call them the column vectors of A. Row vectors of A, column vectors of A. Let A be an m by m matrix, then the subspace R sub n spanned by row vectors of A is denoted by row of A. We call it the row space of A, and a subspace of R sub n, which is the columns, we call it column space of A. We denote it by columns of A. The solution space of the homogeneous, and that's the third one, is called the null space. Take AX, set it equal to 0. The vectors, linearly independent vectors that you get in there, we call those the null space of matrix A. Now, do remember that if you have a linear equation AX equal B, if it is consistent if and only if B is in the columns space of A, which means if B is a linear combination of these vectors that you're going to put in there. And lastly, to put things together, if a matrix R is in row echelon form, then the row space with the leading ones, these are the non-zero, form bases for the row space. Now, these have to be the original. I'll tell you what that means when we get there. And the column vectors with leading coefficients of A of row vectors form basis for the column of A. Now, if they say we're used to finding the basis for the column space, that's what we always find. To find the basis for the row, what you do, take A transpose and do what we normally do, and that'll give you what those are. Again, I'll show you how that works as well. That's not that hard. Just a couple of examples and you see how it works. So let's get with the first case. Let's refresh your memory really quick of what does it mean to have linear combination. Express AX, this is AX, as a linear combination of the column vectors of A, so that's -1 multiplied by -3, 5, 2, 1, plus 2 multiplied by 6, -4, 3, and 8, and the 5 multiplied by 2, 0, -1, 3. That's how linear combinations are written, if you recall. Now, if I take this as well, I want to write this as a linear combination of that. That's 3 times 2, 6, plus 0 times, well, that's really 0, minus 5 times 5, -8. And that's what linear combination mean. You could take those vectors and multiply by constants and get a linear combination of the 2 or the 3 or the 4, depending on what the dimensions are. Let me shift those a bit. Now, determine whether B is in the column space of A. Basically, they're saying take 8x, set it equal to B, and see if there's a solution. If there is a solution, it is. You could find the weights. If not, it's not. So basically what they're saying take 1, -1, 1, -1, -1, -1, -1, 1, and set it equal to 2, 0, 0. Now, as you see, if I take row 1 plus row 2, put the result in row 2, row 1 plus row 3, put the result in row 3, what would happen? So I'm looking at 1, negative 1, 1, and 2. I could take, also I could find the determinant of that to figure out if there's a solution or not, but let's see. That's a 0, 0, 0, 0. Okay, that one is fine. Let me see. 0, 0, 0. Oh, not 0, 0. 0, 0, 0, 2. Oh, we have a problem. 0 doesn't equal 2, so no. This is determine whether B is in the columns of A. No, B is not in the columns of A. B is not in the column space of A. All right, well, here we didn't get a solution. Let's look at the next problem. How about this problem? Again, they're asking, is this a solution? Well, this is a 4 by 4, but the numbers work out nicely. 1, 2, 0, 1, 0, 1, 2, 1, 1, 2, 1, 3, 0, 1, 2, 2, a 4, a 3, a 5, and a 7. Take negative row 1 plus row 3 in row 3. Take negative row 2 plus row 4 in row 4. And 0, 0, 0, negative 1. That's a 1, 3, that's a 4. And obviously we have a solution. X sub 4 equal 4. X sub 3 will be 1 minus 8, negative 7. X sub 3 will be 3, uh, 3 minus 4 minus, oh no, plus 14. So what is that? That's 13, yeah? 17 minus 4. And x sub 1 will be negative 26 plus 4 minus 4, or minus 4 plus 4, I should say. It's negative 26. So basically, this is what we're saying. Take negative 26 multiplied by column 1. Take 13 multiply it by column 2. Minus 7 multiplied by column 3. That's what that means. And 4 multiplied by 1, 1, 3, 2. And you will get a 4, 3, 5, and a 7. That's what linear combinations mean. That's what that matrix is finding for us. Now, let's say I would like to go the other way around. Suppose x1, x2, x3, x4, just like this right here, is a solution of the non-homogeneous. Okay, so that's we know it is a solution. And that the solution set of the homogeneous ax equals 0 is given by those. Let me get those out of the way. X1 equals negative 3r plus 4s. X sub 2 equal r minus s. X sub 3 equal r plus, say, 0. And x sub 4 equals 0 plus s. So basically what we're saying, find the general form of the solution of ax equal, so here they're saying x1, x2, x3, x4 should equal negative 3110 s times 4, negative 101. That's what that means. Normally, we could list those two vectors and say, oh, those form basis for the solution, but that's not what they're asking for right here. What if they told us ax equal b? We just did one of those. That means x1, x2, x3, x4 equals. So let me just check really quick. That equals to b. So in this case, -1, 2, 4, -3. -1, 2, 4, -3 plus r times, and we got the rest, -3, 1, 1. So the only thing that you add would be the constant coefficients of those. There it is. In the next problem, find the basis for the null space and the row space of A. So first things first, if I take this right here and I set AX equals 0, that's basically how to find the null space. So basically, what they gave us, oops, that's 3 by 3. So 1, 2, -1, 4, 1, 3, 5, 3, 2, 2, 0, 2, and 0, 0, 0. And what do you notice? That's x1, x2, x3, x4. You already know there's an extra row in there, right? That's already a given. Anyways, if I take this and I row reduce it, I'll be looking at 1, 0, 1, -2 over 7, 0, 1, 1, 4 divided by 7, and one of the rows 0 out, and we have, of course, another row to 0 out. So if we say x4 is x sub 4, and remember, that's x1, that's x2. So we know x3 and x4 is free. There's x3. Oh, getting excited now. And wouldn't x2 be negative x3 minus 4/7 x4, and x1 be negative x3 plus 2 over 7 x sub 4? So in this case, wouldn't you say find the basis for the null space? So the basis for the null space will simply be x3 -1, -1, 1, 0, and 2 over 7 -4 over 7, 0, 1. Now, any linear combination of those, this book allows for those to be decimal. Most books write it as -2, -4, 0, and 7. They clear the, uh, uh, what do you call it? They clear the fractions. So find the basis for the null space. This is the basis for null space. And don't forget, those are going to stand for the row space. It's that simple. So the basis for row space would be the pivots, the non-zero pivots. That would be the 1, 0, 1, -2 over 7, and 0, 1, 1, 4 over 7. There it is. Okay. B is also a longer one, but the same idea. If I would go ahead and solve AX equals 0, I'll get so if I row reduce that, and you're going to get something like that on the exam. Basically, I want to give you the problem and the solution. I want to know, do you know what that means? And of course, some of those you have to work out. So what does that tell you? That tells me automatically x1, x2, x3, x4, x5. I have 1, 2 pivots. That means I should have 3 of those vectors. So x sub 5 is free, call that x sub 5. X sub 4 is free, call that x sub 4. X3 is free, that's x, and this is not by choice. Wherever the pivots are, you know those are the variables that you can't call free. The rest are all free. But if I look at x sub 2, that is, if you move everything to the other side, that's negative x sub 3 minus x sub 4 minus 2x sub 5. And if you look at x sub 1, that's negative x sub 3 minus 2x sub 4 minus x sub 5. So you look at these vectors and you say the bases for the null space consist of negative 1, negative 1, 1, and 0, 1, 2, 3, 4. There should be 5. Negative 1, negative 1, 1, 0, and 0. There you go. The next vector will be x2, negative 2, negative 1, 0, 1, 0. And then the third one will be x3, x4 and x5. So negative 1, negative 2, 0, 0, and a 1. Those form the basis for the null space. And for the column space, pretty much they're right there. If you want to find the basis for the column space, you would say, well, one, 0, 1, 2, 1, and 0, 1, 1, 1, 2, and there they are. And that's pretty much all there is to it. The hard part is power reducing. Well, we'll do, if it's a big matrix, we'll do that for you. You just need to make sure that you could carry on and figure out the rest. Now, of course, that means any linear combination with those will do, and any linear combination with those will do. How about this problem? A matrix is in Bell echelon form given. By inspection, find the basis for the row space and for the column space. Okay, they're asking for two things. They're asking for the row space and they're asking for the column space, the columns and the rows. Well, let's see. If I run by the pivots, so if I want to figure out the columns, and if I want to know the row, the basis for the row space, this is not like the null space. The null space between the two, you should take all the dimensions. That comes up later on as a theorem. And the last one, we really don't count it, right? The 0, 0, 0, 0. Oh, there's one more. 0, 0, 0, 1. So the last one doesn't count. So we only look for the pivots in the rows, and there they are. So null space and column space, they kind of complement each other. But the column space and the row space, you're looking for rows and columns. Reduce, see where are the errors. Well, again, the same deal. The pivot are right there. So pretty much I'm gonna list each of those row and I'm gonna call that each of these column bases for column space would be simply 1, 0, 0, 0, these vectors, 2, 1, 0, 0, negative 1, 4, 1, 0, and 5, 3, negative 7, 1. And the rows, you look for the rows without the entries with the 1. Well, that's all of them in this case. Okay, let me move the rest. Okay, on 14, find a basis for the subspace of R4, we have three vectors, that is spanned by the given vectors. So if I really want to figure this out, let's see how that works. I would go for 1, 1, negative 4, negative 3. So C1 times this, C2 times this, C3 times that, 2, 0, 2, negative 2, 2, negative 1, 3, and 2, right? And if I row reduce that, I simply get 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, we knew one of those were going to zero out for sure because we have more rows than columns. So the three columns that we're looking at, these form bases for the column space. And we conclude that, let me see, 1, 2, 3. And again, that's going to stand for all of them. We conclude that uh, uh, I'm debating if I should list them or just copy. Yeah, that's so just let me list them again. We conclude that those vectors uh, this set is the basis for the subspace of R4. So these three span I'm losing track. These three are these bases. These three vectors form basis for the subspace of R sub 4, and it's spanned by these vectors. All right. If I look at 16, what are they asking? Find a subset of the given vectors that form a basis for the space spanned by these vectors. Okay, linear combination of those, and then express each vector that is not in the basis as linear combination of the other vectors. So now we're doing a bit more. If I look at matrix A, which is C1, C2 times that, C3 times that, C4, 1, 0, 1, 1, negative 3, 3, 7, 1, negative 1, 3, 9, 3, and negative 5, 3, 5, negative 1. So again, if I row reduce that, this is what I'll get. 1, 0, 2, negative 2, 0, 1, 1, 1, 0, 0, 0, 0, and 0, 0, 0, 0. Now, there is 1 and there's 1, so I'm only seeing 2 of these. So that correspond to V sub 1 and V sub 2. So I could say those two, V sub 1 and V sub 2, form bases for column space of A, and they span V sub 1, V sub 2, V sub 3, and V sub 4. Basically, I could write any of the vectors in V1, in V1, V2, V3, V4 as a linear combination of V1 and V2. I could find that solution. Let me I'm trying to eyeball the solution. Uh, if I take, let me see. If I called this W1, W2, W3, and W4, so I could tell that W3 is pretty much 2W1 plus W2, right? 2 and 1, yeah. And I could say W4 equal negative 2W1 plus W2. And there it is. Yep. All right. So in this case, we know V3 is 2V sub 1 plus V sub 2, and V sub 4 is, getting sloppy with my notation. I gotta be careful. And I could say V sub 4 is actually negative 2V sub 1 plus V sub 2. Okay, let me see. Okay, last problem I would like to look at would be number 18. It says, find the bases for the row space of A that consists of the entirely of the rows of A. Well, let's see, call this A. If I look at the transpose of A, yeah, and if I will reduce that, actually, I was gonna work it out. I'm just gonna copy what's in the book. And what do you notice? The first two remain, right? So in this case, I know that, let me see, the first one correspond to 1, 4, 5, 2, and the second one correspond to the 2, 1, 3, and 0. Okay, I don't know why I put those in there. Here we go. 2, 1, 3, and 0. And we say those form bases for the row space of A. So kind of like you undo it, but you're going from this to this. And that's pretty much all there is in this section.